Okay, so chapter 39 is about matter waves. We're going to find the wave function and also the energy. We have an electron that's confined in a more realistic case, for example, not more realistic, but in a not a free electron, but it is confined in a potential well, and we're going to find how the electron will exist only in certain energies and states. Okay, so and also we're going to talk about hydrogen atom. So let's see. So so quantum physics is about it's about how things work on a subatomic level. As I mentioned, it is more on microscopic level. So particles like electron and protons, they are considered matter waves, and their motions can be governed by Schrodinger's equation. So when you treat particles like matter waves, Schrodinger's equation is the one that governs their behavior. So before we move on, we want to draw an analogy between the wave strings and matter waves. Okay, so when you have a wave, mechanical wave on the traveling on the string, let's say this is two support rod, and this is the length of the string. And when you set up a oscillation, so the string can oscillate, so that wave can oscillate on the string. So there's a wave traveling on the string, and it can, at certain frequencies, then standing waves can be sustained. And this is in a lot of ways very similar to what matter waves will behave when you have an electron that's confined in a potential well. Okay, and with the potential well, the width of the potential well is the length of the string for the mechanical waves. So you'll learn that they're mathematically they are exactly identical. Okay, so let's see. So for free electron, meaning that there's no force acting on the electron and there's no potential energy, then it is similar to the wave traveling along the string of infinite length. So in other words, you have a very long wave, very long, string, and the wave can travel on an infinite, length. And this situation is similar to when you have an electron that's free that can move along the for one dimensional, can move along the x-axis. The free particle can have any value of energy, just like the wave can travel at any frequency. So when you have a free particle, or when you have a free electron, the energy can take up any value. Okay. Now for confined particle, that is when you have a fixed length of the for mechanical waves, when the length of oscillation is fixed, or when you have electron that's trapped in a potential well. So in that case, that is considered, the particle is considered a confined particle. So in that case, it can only exist in a set of discrete states, and each will have a discrete energy. Okay, and this is similar to when you have a wave traveling on a string of finite length. And because if you remember back in 2011, we found the oscillate, when you have a standing wave only at certain frequencies or wavelength that the wave can survive. So it can only support motions with certain frequencies. Okay, so in a way, it's similar to what we call quantized. So this is called confinement principle. And as you can see here, that quantization is due to confinement. Okay, and when you have quantization, energy must be discrete, meaning that the particle cannot have any energy. It can only exist with a certain energy. And we're going to find out, what kind of what kind of condition and what kind of energy level that or energy states that the electron or the particle can have when it is being confined. So this is a diagram. So this is a diagram that shows you that when you have electron that's trapped in an infinite potential well. So for simplicity, we're going to consider an electron that is being confined in an infinite potential well. So this is large, so large that the electron can only be inside this potential well. Okay, and then again we're going to draw the analogies between the a particle trapped in the infinite potential well, and you have the standing wave traveling on the string that of finite length. Let's say these two vertical lines are support rod, and this is the length L. Okay, so you can see there's a directly one-on-one correspondence, and the so only ways classically only ways that the length of the string and the wavelength are related by this can the wave be be sustained and become the standing waves. Okay, so L is the length of the string, and lambda is wavelength, and your n here is the mole number. Okay, or so it's a mole number or no number, mole number. So n can take, so your n is an integer, is 1, 2, 3, and so forth. So you can see that your L does not change, but then your n the quantity n can change, meaning that the wavelength can change. So to be specific, you actually just write down that it is a sub n. So L is equal to m and then lambda sub n over 2, and so for each n number, there's a corresponding wavelength. Okay, and the solution for the displacement, meaning that when you have wave that's oscillating on the string, this is when n equal to 1, it has oscillation like this. So when you have oscillation, then the vertical distance, of course, is the displacement, right? So at this point you have this vertical displacement. At other points, so you can see that the vertical displacement is a function of time and also position, because horizontally that's the x. So you can and because it becomes a standing wave, so we can find out the oscillation, the displacement of string can be described by this expression, which is the y is a function of position, and is equal to amplitude A times sine O m pi over L times x. And your m here is 1, 2, 3, and you can see that the m pi over L, and what we have here is that if you rearrange this, then you would know that this is basically equal to 2 pi over lambda times x. So this is just basically just kx. So your k is m pi over L, and your L is ml over 2. Okay, so this expression tells you that at the boundary, when x equals to 0 or when x is equal to L, there's no oscillation, there's no vertical oscillation, because there's just no displacement in at those two places. Okay, so this is what we call the boundary condition when x equals to 0 or when x equals to L, then there's no displacement. So y is equal to 0. Okay, so now that's so these are the behavior when you have a wave that's traveling on a finite length. So what about, let's say we have an electron that's combined with this infinite potential well. So we're going to treat this electron as a matter wave, and we're going to use the Schrödinger's equation to solve for the solution, and for the wave function, which is the probability wave. And for each, and we know that there's when you treat electron as a matter wave, there's what we call the de Broglie wavelength. So the de Broglie wavelength, by definition, your lambda is equal to h over p, right? And h is the Planck constant, and p is the linear momentum. So if you remember, p is equal to mv. P is equal to mv, and your k is equal to 1/2 kx squared. So 1/2 mv squared. So your p can be expressed as square root 2mk. After you arrange this, you'll know that your p is equal to square root 2mk. Now, when you have an electron that's trapped inside this inside this inside this potential well inside, then there's no potential energy. So so your K becomes E. Okay, so inside this confined system, the Broglie wavelength of electron is H over 2me. So what you can do is that you square on both sides. So we square it on both sides. So you have the lambda square. You have lambda square that's equal to H square, and then over to me. So you can see that this is how you find the energy of the electron when it's trapped in an infinite potential well. So we're going to move E to the left-hand side. So your E is equal to H square, and then over to lambda square. Okay, and your lambda, what we found is that your lambda is actually, although this expression is for classical wave traveling on a finite length, it actually, is the de Broglie wavelength also has to bear that relationship with the potential well width. So your lambda is equal to 2L over m. And so we're going to replace that here. So you have the H square and over 2m, and then you have the 4, and then you have the L square and then n square. So altogether, so after you arrange this, you'll find that your the energy of the electron when it's trapped in the infinite potential well is equal to H square and then n square and then over number 8 times the mass of the particle, and then times the L square. All this are in the denominator. Okay, so this tells you that once you know the de Broglie wavelength, you can actually find out what the energy is, because the wavelength and energy are related to each other. And based on this, we know that the width, the potential well width is actually related to the wavelength. So from there, we can deduce that the energy expression for the electron that's trapped in the infinite potential well is H square n square over AML square. You can see that H square. So let me let's move on to the next slide. So in other words, your energy of the electron when it's trapped in infinite potential well is equal to this expression, and your H square is a constant, AML square, they are both fixed. The only thing that will change is this n, which we call our quantum number in quantum mechanics. So this quantum number, or we call the principal quantum number, and it takes up the integer numbers. So you have the 1, 2, 3, and so forth. And so because your energy is a function of the quantum number, so we need to label, have a subscript to the energy. So you have the E1, E sub 1, E sub 2, E sub 3. All this indicate that that's the energy when the electron is in the state when n equal to 1, or when the electron is in the state when n equal to 2, and so forth. So when n equal to 1, we call this state as ground state. We don't call that the first state. We call that ground state. When n equal to 2, we call that first excited state, and so forth. So you want to make sure that this is how we call when n equal to 1. It is ground state. It's not the first state. First state. And when n equal to 2, we call that first excited states. Okay. So so bear in mind that the n is that. And when you look at these equations again, this describes energy level of the electron. And by the way, so this is what we call the energy level diagram. Vertically that's energy, and we just draw the the horizontal line to indicate the energy. This is the energy for ground state, first excited state, second excited state, and so forth. And as you can see that the energy of electron when it's traveling infinite potential well is proportional to n squared. So with the quantum number gets larger, the separation of the states will get larger as well, because it's proportional to the value square. Okay, so based on this, you can see that we don't have n equals to 0. So what does that mean? It means that when you have a combined system, the electron cannot have states in with zero energy. There's always non-zero, non-zero 0 point energy for the system. Okay, so non-zero meaning that this is non-zero. 0 point meaning this is you just don't have the you don't have an electron with no energy when it's in the ground state. There's always a non-zero ground state energy for the particle when it's trapped in an infinite potential world. Okay, and so that tells you that so we actually derive how the energy can be found by associating by starting from the de Broglie's wavelength, and then you found that this is the energy level of the electron. So what's another interesting that that we often observe is that, let's say, these are the all possible states of the electron that the electron can be at. Let's say we have electron that's right here. Okay, and so when the electron is in the fourth excited state, being that it is excited, so the electron will have a tendency to actually jump down to to a lower energy level. Okay, so that it become more stable. And when it's making the transition, when it's either it's jump up or jump down, during that process, a photon has to be involved. Let's say when you have an electron that's in in this excited state, it wants to jump down to making a transition from the higher level to a low lying energy level. Let's say it jump down to this level. So when the electron making the transition from the fourth excited state to the second excited state, during this process, where did the energy go? During this process, because there's energy difference, you have the E5 here, and then you have the E3 there, so there's energy difference. So the energy difference, you just use this. This is just an example. So that will be my E5, and then minus my E3. So, and then your E, take up this expression, so you can calculate what is the energy difference between these two. So the energy, so when the electron in a high excited state jump to a lower excited state, and a photon has to be emitted. So during this process, there's a photon being emitted. Okay, and the energy of the photon has to be equal to exactly the energy difference of the energy difference of these two states. Okay, so it can only the photon energy has to be exactly equal to delta E. It cannot be it cannot be less than that, less than delta E, or it cannot be greater than delta E. It has to be exact. Now let's say when you have this electron is already jumped down to second excited state, and we want to change the electron from the second excited state to the third excited state. So during this transition, you can see that this electron requires energy in order to make the jump. So where does that energy come from? The energy will come from in the form of a photon. So a photon has to be absorbed. Okay, so when I draw this, it means that we need to inject a photon to the electron, so the electron can make the jump to here. And when you inject a photon, the energy difference the energy difference of the energy required for the electron to make the jump is equal to the energy of the photon. Okay, so for example, let's say when the electron wants to jump E3 to E4 requires just an example, requires 100 that's it requires 5 EV. Okay, and then let's say if you want to give let's say if you inject a photon with the energy of 6 EV, then would the electron jump from E3 to E4? So classically, you might think, okay, yeah, sure. I mean, electron would just take that would just use up the other 5 EV, and then the 1 EV maybe the electron will be then there's just 1 EV left over. However, that in quantum mechanics, it doesn't work that way. If it requires phi eV, the photon energy has to be equal to phi eV exactly. It cannot be less, it cannot be more, because the electron would just not be able to absorb that photon. So in order for the electron to make the transition, the energy difference has to be exactly match the energy of the photon in order for the transition to to be taken. Okay, so we can see that this is the energy difference. The energy difference of the electron is equal to the energy of the photon. And so we can say that like this. So you have the delta E that's equal to the energy difference, and then that must be equal to the energy of the photon. Energy of the photon can be expressed by h times Planck constant. I'm sorry, h times f. So h is the Planck constant and f is the frequency. So this is how you determine the wavelength of the photon, because once you have the energy of the photon, if you remember, this is just hc over lambda. Okay, so that will be the wavelength of the photon. So we talk about this wavelength. We also talk about electrons wavelength. These two wavelengths are different. One is the wavelength of the electron, and one is the wavelength of the photon. And the wavelength of the photon, comes from the energy difference of the two states. Okay, so that's the difference. All right, and so you can see that, as I mentioned, for energy for electron to change states, you can make the change state is either absorb a photon or emit a photon, but regardless, the energy difference has to be exactly equal to the energy of the photon, in order for the transition to be made. Okay, and we mentioned that when you treat electron as a matter wave, then we have to use Schrodinger's equation to find the wave function. And so after you've done that, you start with the Schrodinger's equation for the one-dimensional, and when you have infinite potential well, and inside the well there's zero there's zero potential energy, then you can actually derive the wave function, which is this. So previously in chapter 38 we talked about free particles, so there's no reflection term. But for the particle that's trapped inside the potential well, there's a rightward turn and there's a leftward turn. So when you add them up, that actually give you the solution that's in sinusoidal form. So the wave function, which we use a label, we label that n, because of for different quantum states, you will have a different wave function. So the wave function is is a function of position, and also it is different for different states, and it's equal to a sine n pi over L times x, and n is equal to 1 to 3. Now, if you look at this is exactly the same solution for the wave traveling on the string. So mathematically, they are exactly identical. And as we mentioned, inside this sinusoidal argument, this is just the k, and k of course is related to lambda. So that's why we can utilize the previous equation that we said L is equal to m. What is L? Let me see. We mentioned that L is equal to n lambda over 2, and that's because the solutions are exactly the same. Okay. All right. So so again, when you have electron that's combined in an infinite potential well, this is what we this is our this is our boundary condition, and your the x is between 0 and L, and there's no wave function at the when x equals to 0 or when x is equal to L. In addition to that, there's no wave function outside the well, so the wave function is by default equals to 0 outside that range, because it is an infinite potential well. Okay, and so in order to find the so the next question is, is that you have an electron that's confined in an infinite potential well. What is the probability of finding an electron inside a specific location? Let's say this is infinite potential well, and you have an electron, and this is L, and you have an electron. So the question is, what is the probability of finding an electron in this location, as opposed to you find a probability, within this location or within a range? So how do we find that? So in order to answer that question, we need to start with the probability density. And from chapter 38, you will know that probability density is the probability weight square. So the probability density is that, probability density is this term, wave function square. So when you square it, and then when you multiply that by dx, that gives you the probability of finding electron at the position x. Okay, so probability, the probability, probability is a function of position, which is the wave function square times dx. Okay, and so when when we utilize this, you can see that your wave function is a squared, and then sine, and then this whole thing here is what we call probability density. Okay, right. So next thing is that, so the question is, what is the probability of finding an electron within a range? So probability of finding electron, let's say we want to find the probability, we want to find out the probability of finding electron within the between x1 and x2. Then we will integrate the probability. So you will integrate x1 to x2 and then px, which is and then we place the px by the probability density times dx. Then you have that. So I do also want to mention that the probability of finding electron at the same location, but for different quantum states, will be different. So this is this is illustrated by this diagram. This is when quantum number is equal to 1, ground state, first excited state, second excited state, and and the 14th excited state. As you can see, let's say at this location in the middle, when n equal to 1, we find that there's a very high probability of finding the electron at this location. But when it comes to the first excited state, we found that there's actually zero probability or very low probability of finding electron at the middle point. But when n equal to 3, there's some probability of finding electron this location. Okay, so you can see that the probability of finding electron at the same location will be different when it is in different quantum states. Okay, and based on this diagram, you can see that when n equal to 1, it seems that there's one place that you will most likely find the electron to be at. That's and then there are also some non-zero probability of finding electron at location other than at the middle point, as you can see. But then there's zero probability of finding electron outside the well, and also just like that. And when n equal to 2, when the electron is in the first excited state, you'll find that there are actually 2 places where you'll most likely find the electron. Okay, when n equal to 3, then you got like 3 places that you'll most likely find the electron. So you can see that this quantum number indicate how many the peaks, how many peaks within that well. So n equal to 1, you have 1 peak, n equal to 2, you have 2, n equal to 3, you have 3, and so forth. Okay, now the other thing is that so when n equal to 1, that covers the this, you have that's one wave, and then when like this, okay, upper half the wave. And then when n equal to 2, you just cut the whole thing by half, and then you have that two peaks. When n equal to 3, you just make 2 cuts. Okay, so this is 1 cut and 2 cuts, and then divided by, and then it becomes 3 parts. Okay, so that's an easy way to tell you without even calculation, to find the to know where you will most likely find the electron. Okay, and when in what quantum states. So to find the so let's say if we want to find the probability between x1 and x2 that cover this range, how would you do that? So this will be the probability, right? And so you sum up, you integrate, use this expression and integrate from x1 and x2. Now, what about if we sum up all the probability? If you sum up all the probability, then that will give you 100%, okay? And when we do that, well, instead of saying that is, we can, mathematically, we integrate from negative infinity all the way to positive infinity. And we call this process as normalization. So when you have a normalization, it just means that you sum up all the probability, and that will give you 1, okay? And this procedure will give us the value of the amplitude, okay? So which we're going to show in the next slide how to do that. Before we move on to the next slide, let's go back to this picture. So when you have quantum number that say this is n equal to 15, which is larger than 1, 2, 3, then then what you see here is that this electron, when the quantum when it's a very excited state, because n is a large number, meaning that it has a much higher energy. When you have an electron that's in in the excited state with large quantum numbers, then it pretty much behave like the classical electron as a particle instead of as a wave. Okay, and this is so there's what we call the correspondence principle that is proposed by Niels Bohr. A large enough quantum numbers, the predictions of quantum physics merge with those of classical physics. In other words, when n is large, when n is very large, then the wave feature of the electron will becomes the more like a particle of the electron. Okay, so so that's basically that's what it means. All right, so we mentioned that we want to find out, the wave amplitude can be found by, using the, when we do the integration from negative infinity to all the way to positive infinity, and you sum up all the probability, that will give you 1. So, and this procedure is called a normalization. So how do we do that? First of all, we know that there's wave function is 0 regardless the end, the quantum state. Wave function is 0 when x is less than 0 and when x is greater than L, meaning that outside the well there's no wave function. So we start out with this this definition, normalization, right? And then we're going to replace our wave function with this expression. And then in addition to that, we're going to change the other range, because wave function is 0 outside the range. So we will integrate just from 0 to L, and you have the a squared sine n pi over L times x squared dx. And then this whole thing will give you 1. So you have the 1 that's equal to a squared, since it's a constant, I move it outside. You have the sine n pi over L x squared dx. Now what we're going to do is that we're going to change the variable. We're going to let y equals n pi over L x. And so when you do this, then this is dx, so we need to find out what dx is. So you have the dy, you have the n pi over L dx. So your dx can be expressed by L over n pi dy. So what we're going to do is that so from here we have the a squared, and we have the sine instead of this whole thing, this just be y, and then dx has to be expressed by L over n pi and then dy. And so this becomes this. Okay, in addition to that, because we changed the variable, so we also need to change the range. So when x is equal to 0, we know that your y is equal to 0. When x is equal to L, we know that your y is equal to n pi. So here is my range. Okay, so I have my a squared 0 to n pi, and then sine y squared, and then this whole thing. So again, this is actually a constant, so that can move it outside the integral. So you have the a squared times L, and you have the n pi, and you have this, and then this we have the this we have the solution like this. So we're just going to directly use this will be given. So this when you have the sine y squared dy, this is just equal to 1/2 y minus a quarter sine 2y. So So what we have here is that this is copied down here, and then we're just going to have 1/2 y minus 1/4 sine 2y, and then from 0 to n pi. And so then we're just going to do the plug in the number. So this, you plug in this, and you plug in, and then you plug in this. So you have the 1/2 n pi minus 1/4 sine 2 n pi, and minus, when you plug in 0 here, that's 0. When you plug in 0, that's 0 again. So rearrange this, you can see that sine 2 n pi, that gives you 0. Okay, and so so altogether you have the 1/2 n pi, and the n pi just get canceled. So what you have here is that you have the a square, you have a square times L over 2, that's equal to 1. So then you'll get that your a would just be square root of square root of let me see, what is this, because it's actually covered, I can't see it. Anyway, so you get your a, that is the that is, you get your a, that is the let me see, so n pi, so L, so that will be square root of 2 over L. Okay, so this is basically how you find the a, just by summing out all the probability. So this is when so previously we talked about when you have electron that's trapped in infinite potential world, but most likely the potential world will not be infinite, it might be finite height. In other words, let's say you have electron that's trapped inside a finite potential world. Finite meaning that this does not go all the way to infinity. So when you write down Schrodinger's equation, you will take up this form. Your u will no longer be 0 when it's it has to be, this will be in the equation, and you can solve for the the solution, the wave function, and then from there you can actually figure out the energy level. Okay, now suffice to say that these are the probability of finding electron along the x-axis. So again, still, when n equal to 1 is still 1 peak, n equal to 2 still 2 peaks, n equal to 3, you got 3 peaks. The only difference between the electron trapped in the infinite potential world and the electron trapped in the finite potential world is that the wave function outside the potential world is non-zero. Okay, and because the electron will have the opportunity, will have a non-zero probability, that escape to the outside of the world. So the probability, finding electron outside the potential world is not 0. Okay, so that's a major difference between the electron trapped in the potential world and the electron trapped in the infinite potential world. And then this one, this is when, so previously we talked about electron trapped in a one-dimensional infinite potential world. What about now if we expand it to 3 dimensions or 2 dimensions? Let's say you have electron that's trapped in an infinite potential, infinite potential world, but it's infinite potential, but it's in 2-dimensional. Like for example, like this, it is actually trapped in a 2-dimensional or 3-dimensional. So in that case, because this is the infinite potential world, that would take up this form. You will exactly have the h square am, and then this is the length of the potential world. Let's say for for general in general, the well width might be different in different dimensions. So you will have the and the quantum numbers now, you will have to specify whether that's in the x direction, y direction, or z direction. Actually, let's just look at the 3-dimensional case. So you will have the energy that needs 3 quantum numbers to specify the energy of the electron. Now that the electron is in a 3-dimensional well, so you have the h square, over am, and then you have the quantum number in the x direction, and then you have the well length, in the x direction, and so forth. So you can see that it's symmetric, and then each one has its own length, and each one has its own quantum number. Okay, so that just so this is basically just a we treat that when it's just expand from 1 dimension to 3 dimension. So one other thing I want to mention is that when you look at this, so we can, we can let's say if we have a simplified situations that your energy, the energy of the electron that's traveling in a three-dimensional potential well, has the same, they have the same, width. So you will have the h squared and then over 8m, and then just one symbol, L squared. And then you have the x squared, nx squared plus ny squared, and then plus nz squared. Okay, so in other words, the energy of the electron is specified by the three quantum numbers. So you can see that you have the your nx and ny and nz. So there might be situations that you have the let's say you have the nx is 1, and then ny is 1, and then nz is 2, and then you can have you can have the 2 1 1, or you can have the 1 2 1. What does that mean? It just means that if your nx is 1, ny is 1, nz is 2, it will have energy of let's say energy that just say E. And then when you change the states, that's 1 2 1, it also gives you the same energy. And then when you have the state, when the electron is in the state of 2 1 1, it also have the same value E. And you cannot distinguish which electron is which state the electron is in if you only know the energy, because this energy, for this case, it might have a three different states. So different states can have the same energy as we just demonstrate. These states are called degenerate states. That's just a terminology, okay? It just means that electron, even though let's say the energy of electron, it might be in a different states. It's not just that, okay, it has to be in this state, because the other two will give rise to the same energy, okay? So these states are called the degenerate states. All right, so we talk about when you have electron trapped in infinite potential well, an electron, we briefly talk about the behavior of electron that's trapped in the finite potential well. Now we're going to look at a more realistic case when you have an electron that's trapped in a hydrogen in a potential well that's finite, okay? And one simple example is the hydrogen atom. We know that a hydrogen atom consists of only an electron and a proton. There's no, there's no neutron. So it's just an electron and a proton. And the electron is being confined to the proton because, between them, there's an electric force. We call that Coulomb's force that's binding them together. One is, proton has a positive charge, electron has a negative charge. So when, so the Coulomb force is attractive force. And when there's a force, then of course there's a potential, and the potential of course takes up this form, which is 1/4 pi epsilon naught Q1 Q2 over R. R is the separation between the electron and the proton. Okay, so substituting the charge here, you can see that the potential energy is equal to -1/4 pi epsilon naught and then E squared over R. Okay, and this diagram and this tells you that when R approaches infinity, there's no electric potential energy. And that makes sense because when you have an electron and a proton that's so far away, then the force exerting on one another is basically zero. So that is like no force, and then so there's no electric potential. So that's say you have an electron that's trapped in in this potential well. Okay, so this is a potential well. As you can see, when R approaches infinity, your U, it is approaching to the zero value of U. And when R is so close, when R is so small, which means that the electron and proton are so close, you can see that the potential energy gets larger. Okay, and so this is, as you can see, this is like a potential well. Let's say when you have an electron that's trapped, that's in this potential well, then what is the energy level of the electron? And as we mentioned, the electron, when it's being trapped, when it's being confined, it can only exist in certain states. And with that state, it had, it comes with a certain energy. Okay, In other words, the energy of the electron is quantized. Okay, so how do we find that? We start with the Schrodinger's equation, and when you have the Schrodinger's equation, and then you have the potential energy that takes up this form, and when you derive the and then solve the Schrodinger's equation, we'll be able to find out the wave function and also the wavelength, and from wavelength you will be able to deduce the energy. So so the quantized energy, after you've done that, then the energy of the electron takes a very simple form that's equal to negative 13.6 eV over n squared. So this expression will give you the energy in eV, and n here is a quantum number, okay? And negative 13.6, that's the one that's for the hydrogen, because after you plug in those constants, that give you this, okay? So it tells you that the energy of electron in a hydrogen atom is quantized, and the base value is negative the base value is negative 13.6, and with a larger n, with a larger quantum number, you'll see that your energy gets the energy gets smaller and smaller. Okay. So let's look at so this basically shows that this is the equation that tells you the energy of the electron. And so an interesting thing of the energy of the electron is that, as we mentioned, electron can change states, and during the change of states, it will emit or absorb a photon. And some of the energy of the photon actually is in a range of visible spectrum. So when the electrons making the change, we can actually see the spectrum. And each atom has its own signature of spectrum. In other words, let's say hydrogen will emit a visible spectrum like this, and then so for other species, it will has its own spectrum that different colors of light that when that will occur when the electron is being emitted by the electron, when electron changes its states. So this is how we, this becomes very useful, because you can actually observe a distant star and look at the spectrum in order to deduce, what kind of element that is on that planet, the distant planet, just by studying the the spectrum of what you observe. Okay, so so basically, when electrons making changes states, it can absorb a photon or emit a photon. When it's absorb the photon, meaning that it's jumping from lower energy state to higher energy state. When it's emitting a photon, it is jumping from high energy state to low energy state. Okay. So we have what we call the absorption line or the emission line. Emission, of course, is when the electron emit a photon. Absorption line is when the electron is absorb a photon. What we found is that when electrons changing states, when they start when one of the changing state indicate there's the energy difference between two states. If one of the energy state is n equal to 1, the ground involves the ground state. This kind of lines are group are called the Lyman series. And when one of the states involves 2, then it is called the Barman series. And when one involves a number quantum number 3, it's called Paschen series. So you can see that you have the Lyman series, Barman series, and Paschen series. The only one that will be in the visible spectrum is the Barman series, and this is the emission lines. As you can see, this is when this involves the change of state between between 3 and 2. This is the one between 4 and 2, and this one is between 5 and 2, and so forth. And this one, Lyman series, that involves that when you have 2 to 1, and then 3 to 1, and then 4 to 1, and things like that. So you can see that the change in energy, the difference of the energy, let's say you know, that E an initial state, let's say just say initial state. Let's say that would just be the energy difference is just the final energy state minus initial energy state. And then we're going to take the absolute value because you know, because it is we just want to know the energy difference. And so when you have this, and then you remember that, you know, your energy of election is negative 13.6, right? And then let's say this is the NF square, and then minus negative 13.6, and then Ni square. Okay, so to find the energy difference, basically you know that will be just the energy difference, and then the energy takes is this form, negative 13.6 over n squared. So plug in the number, you have the negative here. So when you do this calculation, and then that just give you the energy difference. That's in EV, and has to be equal to the energy of the photon. So whatever value you go, and that will give you the hc over lambda. And this lambda is the wavelength of the photon. Now, I do want to caution you that when you do this, this is in EV. And when you set this up, if you want to calculate the wavelength of the photon, either you change EV to the joules, or you use a Planck constant that's in EV, so that the units will be consistent. Okay. So this tells you that when electrons when electrons change in state, you can have produce emission lines or the absorption line. And the spectrum of atoms, not just for the hydrogen, the spectrum of atom, that actually is a signature of the atom. And so once you study their spectrum, you know, if you study a spectrums of unknown species, and then you can identify what kind of species in on the planet if they have the same spectrum like what we have on Earth of the elements on Earth. Okay, so let's see. So moving on, I do want to mention that, you know, a lot of you kind of when people are talking about, you know, how the electron orbiting around the nucleus, usually this is the picture that often shows up, you know, when you have for the hydrogen, the simplest case is the hydrogen, that you have a proton situating at the center, and you have electron, and this orbiting around the proton. So this is like a planetary motion. And so this picture is not completely right, because it will violate the uncertainty principle. We can't have unlimited precision knowing where the electron is. There's always it's pretty fuzzy, meaning that there's always probability you cannot know with unlimited precision, you know, that the electron was just orbiting around this with no the electron might be found here, there, but not necessarily just, you know, on this orbit. But there's the probability of finding electron on this orbit is apparently much higher. Okay, that's basically what this picture shows you. And so this is what the famous Bohr's model of a hydrogen atom. He assumed that the electron is a particle that moves in a planet-like orbit around this nucleus, and he was able to predict the energies of the quantum states of a hydrogen atom, and found the effective radius of the hydrogen atom, which is what we call the Bohr radius. And this assumption is inconsistent with the uncertainty principle. And later I'm going to show you the picture. You know, if you calculate use the probability density to calculate the probability of finding electron at the specific location, you'll find that it is not as simple as like this. Close, but not exactly like this. And this is when the quantum number is large, and then you can get the it's like you can just treat, or when when the it will just be I wouldn't say quantum number is large, but basically this is this is when you most likely find the electron here. Okay, all right. So in fact, let me just bring up the picture. So this is basically when you use the probability density to calculate where you most likely find the locations of the electron. This just tells you that, you know, so when you have the ground state, the electron, you can see that it is you know, congregate like this, but all these dots indicate the probability. So we can see that you know, the more dots indicate, the more likelihood you'll find the electron to be in that location. And this is when n equal to, you know, n equal to, you'll find that, you know, the electron will most likely be found here, and also there's a one place there. And then this is again, you know, the first excited say n equal to 2, but then you have a different parameters that, you know, indicate that the distribution, you know, finding electron, you know, the picture is different from that and that. And this is when n is very large. And in fact, this is when n very large that, you know, you can find the electrons almost like congregate. The probability of finding electron, you know, is pretty fixed. So in a way, the Bohr, the Bohr picture, sorry, the Bohr picture of the hydrogen atom is actually this is actually the picture when n is quite large, that you'll find that electron will most likely be found in this orbits. Okay, all right. So so this picture shows you that I got, you know, there are several other quantities, and these are what we call the quantum numbers. So let's move on to that. So for a hydrogen atom, 3 quantum numbers need to be used to specify the state of the electron. So quantum number, the principal quantum number is not enough to specify the state of the electron. We need additional 2. And the additional 2 are the you know, the L and ML. So let's go through you know, each one of them. So N, of course, we know that is called the principal quantum number, and that specifies the energy of the state. L is what we call the orbital quantum number, and that is the magnitude. That's the magnitude of the angular momentum associated with the quantum state. And the L is always less or equal to n minus 1. So once you know your n value, you pretty much specify your L, because you know the range of L, because your L has to be equal or less than n minus 1. And ML is what we call orbital magnetic quantum numbers that's related to the orientation of in space of this angular momentum. And your ML is equal to 2L plus 1. So in other words, if you know your L number, then there are 2L plus 1 possibility for the ML. Okay, so altogether, you need 3 quantum numbers to specify the energy, to specify the states of the electron for a hydrogen atom. However, when you're dealing with other atoms, then we need additional quantum number to specify the state, and that quantum number is the spin magnetic quantum number, which we call MS. It takes up 2 values. It can either be 1/2 plus is what we call the spin. So it's either plus 1/2 or negative 1/2. Okay, so the electron has intrinsic spin angular momentum, which called spin S. So usually we use the thumbs up indicate 1 plus 1/2, thumbs down indicate minus 1/2. So when you have, let's say, when you have helium. Okay, take for example, when you have a helium, which is not hydrogen, then you need 4 quantum numbers to specify the state of the electron. And why do we need that additional states? Because electron does not like to be in the same state. You can have an electron that has a full have the 4 quantum numbers the same. The last one, MS, has to be different. If you have the preceding 3 quantum numbers are the same, your MS can either be spin up or spin down. It cannot be both spin up. It cannot be both spin down. One of them has to be different, and that is because Pauli's exclusion principle. It says that no 2 electrons can occupy the same quantum states. Okay, at least one of the quantum number must be different. Okay, so that's why If one has already spin up, then the other one has to be spin down. So electron, protons, these are the what we call the fermion. Fermion have the up multiple of half an integer of the spin. Now for photon, photon is what we call boson. Photon like to congregate. So photon does not specify. You can have as many photon in the same state, but then for electron, they cannot have the same state. When they occupy the same same state, it cannot occupy the same state because even though you have the preceding three are the same numbers, the last one has to be different. Okay, and that's due to the Pauli's exclusion principle. So this is just for your information, and when you solve for the wave function, utilize starting from the Schrödinger's equation. This is the solution. The solution of the solution of the wave function as a function of the radius, and that's equal to 1/, square root pi, and a, which is the number, and then 3 halves in the arguments, and then e to the minus r over a. And a, this one is, as you can see, it's a constant, and after you plug in the constant, that gives you 52.9 picometers, and this is what we call the Bohr radius. Okay, and this is the what we showed earlier, the Bohr radius. So you can see your wave function, so function radius is actually e to the minus r over a, and so the probability of finding electron in the volume, differential volume dV, can be described by this. So you square this and then times dV. So when you square this, you get and then multiply by 4 pi r squared dr. That's for spherical for a sphere. Then you have 4 over a cube, then e to the minus 2r over a, and then r squared dr. So this is the wave function. This is wave function. This is probability density, and then you can integrate that to, when you integrate this, that will give you, so the probability of finding electron at radius r will just be this. That will be just equal to 4 over a cube r squared, and then e to the minus 2r over a. So when you integrate that from 0 to infinity, that will give you 1. And so this is basically how you find the probability. So once you have probability, integrate between from one location to another, that will give you the probability. And this is how we build up the what is the probability of finding electron. And you can see that it is quite fuzzy. It is not like you can just describe that as a planetary like motion. That will work only when the quantum number is large. Okay, so I basically conclude this chapter. Yeah, already.